Hello everyone, so today we're going to go over a rotational kinematics problem. So if you're in Unit 5 rotation in AP Physics, or if you're in whatever section you are in other physics classes, this is a great video for you. So this problem comes from the rotation chapters, the first rotation chapters of the Cut Nail book, just in case you want to know where you can find it, and it kind of relates to biology. That's why it has this you know what it is. Some bacteria are propelled by biological motors that spin hair-like flagella. A typical bacteria motor turning at a constant angular velocity has a radius of 1.5 times 10 to the negative 8 meters and a tangential speed at the rim of 2.3 times 10 to the negative 5 meters per second. Now, the first question, because there's two questions right here. What is the angular speed? The magnitude they specified here of the angular velocity of this bacterial motor. And then the second question asks, how long does it take the motor to make one revolution? So we're gonna do A. We're gonna do A in blue. So one thing that is essential for your success in any physics problem is writing down your known values, functions, equations, anything that could possibly relate to this problem that is given to you. We know that a typical bacterial motor turning at a constant angular velocity has a radius of 1.5 times 10 to the negative 8 meters. So we know that the radius is 1.5 times 10 to the 8 meters. To the negative 8, meters. Then it says, and a tangential speed of the rim, meaning this is like your regular, what they mean by tangential speed is kind of like your regular velocity, your linear velocity per se. Linear velocity is 2.3 times 10 to the negative 5 meters per second. Don't forget your units. Now, they're asking us for the first one, what is the angular speed? Now, the symbol for angular speed is lowercase omega, which kind of looks like a slanted W per se. So this is the one variable we don't know. To kind of picture this in a way, let's say that this is a bacteria in like the flagella. It's turning basically. So the radius of it here it's r, which is this same thing right here. I'm trying to make this seem like it's like in motion, but if we were really to picture, this would be like, let's say this is the bacteria, and then this is the flagella, let's say, and this is like the whole circle that it's going around in. I mean, it's not really proportional, but hopefully you get it. This is the path the flagella follows. So like this is the path right here, this thing right here. Now we know that the distance from the center of a circle to its from the center of the circle to its border, lack of a better word, that's the radius. And they provide us with the tangential velocity, which is always perpendicular to the circle. So, and this is the tangential velocity. However, what they're asking us for is the angular velocity, which would be fast. It like goes around in a circle basically, like the speed of it, like when it goes around in a circle. That's kind of like a way to visualize it in a way, if you want, if it helps you. Okay, so now there are different equations for rotational kinematics, and they all can relate to the regular kinematics equations that we know of. So in a way, there's always like equations that, for example, for like angular velocity, there's an equation that connects with tangential velocity, which is the same thing as saying like linear velocity. Same thing for acceleration. There is angular acceleration, and there's usually an equation that connects with it that's linear acceleration. Now, in this case, the equation that we can most definitely use, since they give us the radius and the tangential velocity or linear velocity, there's one equation that is the angular velocity equals the linear velocity or tangential velocity over its radius. This will always be true. So from here you can get, the radius is the same thing as the linear velocity divided by the angular velocity. Or if you move it around again, you can get the linear velocity equals the angular velocity times the radius. So in case you guys want to write it down, these are really good in case you ever have this problem. So they're asking us for the angular velocity, and we have the equation for it, and we have both values that we can use for it. Now, if for some reason we're gonna use this equation, and we're gonna plug in the values that we already have, that we have written down, because we are super resourceful and we know what we're doing. So we're gonna get our tangential velocity right here, and we're gonna sub that in for the v in this case. Now, usually when I sub in, I usually do parentheses. Now you don't really have to. If you're really running out of time, just plug it in, or maybe even plug it in your calculator and just keep going. Don't look back. Your life is not going to end, but at least show what you have plugged in, because that can help Mr. Lazarbe or the AP graders to see what your work is. We know the value for radius, which in this case is 1.5 times 10 to the negative 8 meters. Right here. Oh, not that. Right here. And now we have plugged it in. It's all ready to go. And if you're really good with scientific notation and dividing, then awesome. I'd rather use a calculator in just in case. So we know that the angular velocity, aka our fancy W or lowercase omega, equals 1.5 times 10 to the third power. And now the units for angular velocity are always radians per second, as far as I've used. Do not forget your units. Probably Mr. Lazari has drilled this into your brain, or your physics teacher, but do not forget to label your units. It can change the whole meaning of a problem. Okay, so for part B, which is going to be in red, it's asking us how long does it take the motor to make one revolution. So it's basically asking us how long does the motor take to do like one circle, like to really dumb it down. So how long it takes to go around, like to do that once, to make one revolution. So like to go around in a circle once is one revolution. Therefore, we know that one revolution, that 2 pi radians is one revolution, because pre-cal and stuff, to go around in a circle, yeah, it's 2 pi radians. So to do one revolution around a circle is 2 pi radians. As I said before, there's equations that relate angular rotational kinematics with each other. So there's one that we can use that's super useful, that is your angular velocity will always equal your angular displacement over time, because it's kind of the same thing as saying like your velocity equals the total distance that you have done over the time that it's taken. So like meters per second. So this one would be, so like however many meters per second, like per se, because you can base it off of the units too. So same thing here. So the units for angular displacement is radians, and the time is the same thing. So it's radians per second, which is the units for angular velocity. It's crazy how they all go together. So we do have our angular velocity right here. We do have that because we solved it before in the problem before that. How convenient. Look, it's right here. So at least we know that our angular velocity is 1.5 times 10 to the third radians per second. So this is one of our values. Now we're still missing our angular displacement and our time. And what they're asking us for is how long. So basically how long, meaning like that's the time, like how long does it take? So it would be the time, the total time that it takes the motor to make one revolution. So if you want, you can rearrange this equation already to have time equals angular displacement over angular velocity, because these switch. That's a trick. I don't know if you know, but you don't have to like multiply it from both sides. You can just switch this one with this one and you'll be right. So we don't know what our angular displacement is, but don't fret, because it only take, it tells us right here, 1 revolution, meaning how many radians does the flagella cover in 1 revolution. So we know that since it's going around in 1 revolution, we know that the theta, like, look, it's already here. So this means that every 1 revolution, you do 2 pi radians in like the distance that goes around in a circle. So that's the angular displacement. So, and it's telling us in 1 revolution. So luckily we can already say, oh, you know, since it's 1 revolution, I know that its angular displacement has to be 2 pi radians. So now we already have our 2 variables, and now we just plug and chug. So we have our time here, which we don't know, which is the thing that we're trying to find, and we have our angular displacement and our angular velocity. So what we're going to do now, we're just going to plug and chug. Remember, try to keep your units. If you want to do the parentheses, if you don't, just do whatever works for you. 1.5 times 10 to the third radians per second. We know that time in this case is in seconds. Sometimes they may ask you in minutes or something, then you have to convert, but luckily it's just in seconds. All our units are in seconds. So units wise, you can cross out this, and you should get 4.2 times 10 to the negative 3 seconds. And don't forget your units. It's always essential. And this will be your answer for part B.